the mathematicians. Let's have a look at the next bit. Complex conjugate of a Cartesian complex number. The complex conjugate complex number is found by changing the sign of the imaginary part j. Okay, so simply the same complex number, but with the sign changed that's in front of the j part. So if we look at this first example here, 3 plus 2j, the complex conjugate of that is 3 minus 2j. Minus 5 plus 4j, the conjugate is minus 5 minus 4j, and so on. What I'd like you to do is just spend 5 or 10 minutes doing those multiplications, okay, and getting a result for me. So if we do this on this one, that's 3 times 3 is 9. Let's write it down like that. No, let's write it like this. 3 times 3, 3 squared. Yeah. 3 times minus 2j minus 6j. 2 times 2j times 3 is plus 6j. 2 times minus 2j is minus 4j squared. Those two cancel out. That becomes 3 squared plus, and because that's worth minus 1, that becomes plus 4. Or we could write that as 2 squared, couldn't we? The point I'm trying to show here is that it's 3 squared plus 2 squared is the constant 13. Okay? All of these, the answers to all of these, this one is minus 5 squared plus 4 squared. This one is minus 2 squared plus 8 squared, and so on. When you multiply by the complex conjugate, you cancel out the j term, okay, and the result is the two constants a and b squared and added together. That's equal to a squared plus b squared. So by multiplying a complex number by its complex conjugate, i.e. the same vector with the angle, the sign of the angle changed, we cancel out the j term. Let's think of this in terms of a vector diagram. I draw that like so, and I say this is my vector. Alright, and then, I'll be quite clever with this actually, I think. If that's, let's imagine that's 3 plus 2j, the complex conjugate of that is, change the sign, so if I flip that on the up-down axis, I didn't want to do that, I want to copy it first, didn't I? Control Z, Control D, and that is 3 plus 3 minus 2j down there. The complex conjugate. If we parallelogram those, we'd end up there, straight along the x-axis, and we cancelled out the imaginary part. Yeah. Right. Everybody happy with that? So that's what the purpose of doing this is that it becomes useful when we want to do complex division, which is on the next page. Okay? So, division of Cartesian complex numbers. It's achieved by the numerator and the denominator. What we do is we multiply the numerator and the denominator. So it's multiplying in there, beg my pardon, multiplying the numerator and the denominator by the complex conjugate to remove the imaginary part in the denominator. So what we have to do, and get you to do some of this, is we have to take this complex number 2 minus 5j over 3 plus 4j, and we have to multiply the top and bottom by the complex conjugate of the denominator. So we've got to go the bottom multiplied by 3 minus 4j. If we do that, what must we do to the top? Do the same thing. So we've got to multiply the top by 3 minus 4j. The answer to the bottom half is let's write it out though, that's 3 squared plus 4 squared. We know that from what we've done on the previous page. If you're uncomfortable with that, multiply it out and prove it until you are comfortable with it. Okay? Would you prefer I wrote it out? Yeah, they only cancel out if the j terms are the same size but the signs are different. Because then what you get, let's write it out. It is 3 times 3 is 9. 3 times minus 4 is minus 12j. 3 times plus 4j is plus 12j. And then plus 4 times minus 4 is minus 16j squared. Yeah? These two cancel to disappear, don't they? Yeah? And that one, that j squared, changes the sign of that number. And that number is just the 4 squared. So it becomes, this becomes plus 16, that's 9 plus 16 is 25, that bottom line. Yeah, everyone happy with that? Top line is, tell me how I do it, Paul. Top line, numerator. It's 6. 2 times minus 4j is, yeah, times, there's no j with that 3, 5j times 3, careful, Minus 4 times minus 5. Plus 20 j squared. Yeah? Okay? Yeah? Everyone happy with that? Everyone agree? Got there in the end? Right? So then let's bring together any like terms. What does the j squared do to this? Makes it minus 20. So the top line becomes 6 minus 8 minus 15 is 23j, and we said that becomes minus 20. So write that out like that. Underneath here, we've already said that's equal to 25, because that's that. This becomes 16 minus plus 16, so 9 plus 16 is 25. Everyone agree with that? So we can bring these two constants together up the top here. 6 minus 20 is minus 14 minus 23j. Yeah. Minus 23j on the top line. And we've got 25 underneath. Okay. What we can do is say that is equal to minus 14 over 25 minus 23 over 25j. Or we can turn those into decimals. Because they've got a j attached to that. Right? Just on your calculator, minus 14, if you prefer it, minus 14 over 25 is 0.56, and just 0.56 or minus 14 over 25? Minus 0.56. Minus 23 over 25. Yeah. So you could have leave your answer in that form, the thirds, or put it in decimal form. I'm assuming they are both rounded to two significant figures. Yeah. They are exact, are they? Okay. Alright, so I expect you guessed it. Have a go at them too. Right, gents, so what have I got to do to this then? First thing I've got to do. The complex conjugate, yeah, which is we'll do that to the bottom. I've got to do it to the top. Yeah. We can multiply it out manually if we want to, but we know what happens to the bottom. What happens to the bottom is equal to it's equal to 3 squared plus 4 squared. That's equal to 25. You know that. And the top line, how do we do that, Kyle? Remember what the process is. Multiply out brackets. We multiply out brackets. We multiply everything in one bracket with everything in the other bracket. So we do minus 3 plus 4j is plus 4j. Minus 3 times minus 3 plus 9j. Minus 3 times plus 4 is minus 12j squared. Yep. Negative number times a positive number is a negative number. Move them down a bit for a minute. Okay, so the resultant of that is, what does the j squared do to that? Makes it plus 12. So we got this bit here. It would be blue. This bit here. Tidy it up a bit. Minus 12j becomes plus 12. Yep. So as the top line becomes minus 3 plus 12, which is minus 3 plus 12. That bit, the j squared in there, turns that minus 12j squared into plus, just a constant, plus 12. Yeah. So this minus 3 plus 12 is 9. 4j plus 9j plus 13j over 25. Who's pushed the buttons on that to turn it into a decimal? 9 over 25 is... You can leave it as a third if you want. 0.36. And 13 over 25 is... So that's that one. Yeah? We've got the top line of this one from the previous question. From earlier. Z1 times Z2 is 13 plus 11j. So this is equal to 13 plus 11j over Z1, 1 minus 3j plus minus 3 minus 4j, or Z2, minus 2 plus 5j. So what we got to do there first? Yeah, that's the denominator. That's the result of Z1 times Z2 that we had earlier. Yeah? What we got to do now? You've got to turn that denominator into one complex number. You've got to do that addition on the bottom first. So we've got to do 13 plus 11j on top. How do we do this addition now? One plus minus 2 is 1 plus minus 2 minus 1 minus 1 minus 3 plus 5, minus 3j plus 5j minus 3 plus 5 2. Go back to the number lines if you don't get that. Yeah, everybody happy now? Next bit to do is multiply by the complex conjugate. So we've got to do this. Minus 1, minus 2j on the bottom, minus 1, minus 2j on the top. This bottom line quickly multiplies out to 1 squared plus 2 squared equals 5. Yeah, but minus 1 squared is 1. And the top line, what we got to do, I'll multiply out the brackets. So how do we do that? Minus 13, well done, yeah. Minus 2 is, yeah, j, don't forget the j, yeah. And then j squared. Yeah? Right, well done. And pointing out the following time, this bit here is equal to plus 22. Yeah? So that top line becomes minus 13 plus 22 is 9. Minus 26 minus 11 minus 37 j all over 5. Yep. Nine over 5 is 1.75 even. What? No, 1.8. Yeah, 1 4/5. 1.8 equals 1.8 minus 7.4 j. Okay. By the way, we might come to something later. If the complex number has got units, so if this was volts, the units would go there. So it would be 1.8 minus 7.4 j volts. All right? Or amps or ohms, whatever the units were. So when we get to science in particular, and if I give you an engineering related question in this maths where there are units involved, putting the units will be important. Everybody happy with that and what the process is? Okay. Going to move on now then. The next bit. The polar form of a complex number. Already touched on it a little bit. Now we're going to have a bit of a closer look. If we let a complex number z be represented by the complex number x plus y times j, as shown in the diagram, the distance OZ there let that be r, and the angle that OZ makes with the positive real axis, this angle in here, equal theta, then by Pythagoras' theorem, the length of that line r is the square root of x squared plus y squared. You all remember Pythagoras' theorem? The square on the hypotenuse is equal to the sum of the square on the other two sides. Okay? So the full Pythagoras theorem using these letters is r squared is equal to x squared plus y squared. So if we want to find r, we just square root the other side. Okay? And you should already be reasonably familiar with Pythagoras' theorem anyway. We did touch on it, I think, a little bit earlier. Okay? And then, also, using trigonometry, the ratio involved with the two sides x and y, the rectangular form sides, the horizontal component and the vertical component, is that the tangent of the angle theta is equal to the opposite side y divided by the adjacent side x in this case. So if we want to find the angle is the inverse of that tangent, as tan to the minus 1 of y over x. And that angle can be expressed in either radians or degrees. So mathematicians call r the modulus. As an engineer, I tend to think more of it as the magnitude, the size of that vector. How many amps is it? How many volts is it? Okay? If we have it in rectangular form, as x plus j, yj form, it doesn't tell us directly how many amps or volts it is. We need it in polar form to know the magnitude of that vector. Okay? When we want to write just about the magnitude, we put so if we've got a vector z, we write the magnitude of it as z between two horizontal lines like that. That means the magnitude ignoring the angle. That's the length of that line. Theta, in this case, is called the argument by the mathematicians. So we've got a modulus and an argument. As an engineer, we more like to think of the argument as the angle of that vector from 0. Okay? Same thing, but you're going to see the mathematical terms in textbooks about engineering maths as well, so it's important to know what they are. So a full complex number in polar form is written like that. The complex number z is the magnitude of that vector at an angle of theta degrees or theta radians. Okay? If we are talking about an impedance Z in ohms, you'd write it as Z is equal to the magnitude of that ohms angle theta degrees. The units go between the magnitude and the angle symbol. Yep. So that's how we write, and that's how polar form of these angles work. And the angle is about it being positive angles go anti-clockwise around circles, starting from. So if this is our axis here, 0 degrees or 0 radians is there. 90 degrees or pi over 2 is there. So positive is anti-clockwise. Down here, minus 90 degrees minus pi over 2 in radians. So negative angles anti-clockwise. Okay? So we normally deal with up to minus 179.99 and up to 179.99 in that direction. Okay? And this over here is 180 degrees or pi radians. All happy with that as a way that we would express a vector in polar form as a magnitude at an angle. So on the following page it says determine the modulus and argument of the complex number z is equal to 2 plus 3j and express z in polar form. Quite often useful to sketch the problem so that you know what quadrant you are in. Here we go on 2 on the x-axis, positive 3, so we're in the first quadrant. Our angle is going to be between 0 and 90 degrees. Calculator in degrees mode, please. Right, gents, so r is equal to what? Yeah, but tell me how you do it, Lewis. That's to 3 significant figures, yeah? So that's found r. Yeah, the length of the line. No, finding the length of the line has got nothing to do with j, has it? That's just the length of that line is the square root of 2 squared plus 3 squared by Pythagoras theorem. If you're doing this manually, you've got to find the magnitude using Pythagoras theorem and the angle using tangent ratio of trigonometry. Remember previous page? But how are you gonna? Why would you do that? All you're interested in is the length of these 2 lines, there and there, to find the magnitude of that, the length of that line. It's just a right angle triangle problem. All the j does here is help me to know that that's a vector in that quadrant. To find the length of that line, it's simply Pythagoras theorem like that. So it's 3.61 units long. Yeah? The j term just helped me draw that diagram in this case. Yeah? So the magnitude of a polar complex number is the square of the real term plus the square of the magnitude of a j term, all square rooted. Yeah? But it won't do anything, will it? Yeah. So, how do I find that angle, Paul, without the calculator? I do it like this. Tan theta is the opposite side of that triangle, which is the 3. Length of that line is 3. divided by 2. Yeah? Therefore, theta is the inverse tan to the minus 1 of 3 over 2 equals, no doubt someone will have done that, 56.3 degrees to 3 significant figures. So when you do that conversion, Paul, that's what your calculator is doing, separately those two calculations for you. Tan minus 1, 3 over 2. Yeah. So the full answer to this in polar form. Okay. Therefore, 2 plus 3j is equal to 3.61 angle 56.3 degrees. Yeah, but my only argument about that is that you've used, to do it using the sine rule, you've used that rounded result from there. Yeah? Whereas if you use the tangent, you're using the two given values in the complex number. Right? But no, that's what did you get? That's not far enough out to make, you wouldn't lose marks for that. Alright? That's along the lines of like what I said before. If you can use given values, use them. Dom, alright? Yeah? On the next page, there's 4 there to have a go at. Think about what quadrant they're in, and the little diagram is there to help you with what the angle is. Alpha is equal to 180 145 minus 145 plus 90 equals minus 55 degrees. So then how do we find what we're looking for? It's the horizontal component x and the vertical component y. Which one is 7 sine 50? What? Is it 50? That is 55, isn't it? Yeah. What's that? So you reckon the answer is 5.73 take away 4.01 J. Who agrees with that? I've got a problem with it. What's the problem? Yeah. By drawing the diagram, I've shown you that both the imaginary J part and the x part are negative. Minus 5.73 minus 4.01j. Alright? If we didn't draw the diagram, you might miss that. That's in that third quadrant, and both parts are negative. When you do that on the calculator, that'll work all that out for you. When you do what on the calculator? Yeah. What does it do if you put in 7 times the sine of minus 55? Sorry? When you do what? Yeah. 4.01. Yeah. You can't rely on putting minus 55 degrees in the calculator. But when you use the conversion that I'm going to show you in a minute, that'll do that all in one go, and that'll give you that answer. Yeah. All right. So that's the manual way to do it, but it does rely on you knowing about the 4 quadrants and how the complex numbers fit into that. Use the calculator to convert between polar and Cartesian forms. Now, I only know how to do this with Casio, so hopefully you've all got Casios. Make sure your calculator is in degrees mode. Hang on, no, go into radians mode, please, for this page. We're going to convert, first of all, 6 angle 1.23 radians into Cartesian form. You push the shift key. You push the key with rec on top of it. On my calculator, it's a -1. Shift rec. You're saying you're converting to rectangular. In the brackets, you put 6, and then you push shift, and the comma, which is on top of the closed bracket symbol. And then you put in the y part, the angle part, which is 1.23 radians. Close the brackets and press the equal sign, and you should get hang on. I'll tell you lot. So we do shift, rectangular, 7, comma, -145. Close the brackets. We get an x of minus 5.734 and a y of minus 4.015. 145. You need to put your calculator back to degrees, Paul. We was in degrees for that one. Trick question. Yeah, both negative. Make sure you look carefully at the signs. Yeah. Okay. So the calculator converter handles all that issue over positive and negative angles bigger than 90 degrees for you.